it will be also mostly online, as I understand.
I see. Yes.
Yeah, so there were many cancellations,
But is it going to be so online?
Yes, it will be. It will be partly online. You can come there, but I think most of the people will participate online.
What's about satellites?
Good question. I don't know precisely. Probably some of them will go online. Some of them would be canceled.
Yeah, because there were a lot of them.
Yes.
Planned.
The satellite in memory of Dubrovin, but I don't know, is it cancelled or not?
Where it was it was planned. I heard something about it.
Zagreb, somewhere in Zagreb, or in Trieste.
In Zagreb, Trieste, yes. Yes, it's very close to the place of ECM. Yeah, I was there 2 years ago when it was organized, this conference. It's a pity because they were very well prepared, and the place is fantastic. The place is fantastic, just on the near the sea. So it's a very nice place.
Yes, very nice. I know.
You know, you have been there, yeah? Porto Rosa or Porto Rosa.
As a young man, I know.
Really? So you know this place?
The place is very nice, and it's very close to Trieste. Maybe 1 hour.
I see.
1 hour, maybe from Trieste by car or by bus.
Okay, so I think now it's time to make preparations.
Okay.
I think so. Rustem. Нету его.
Yes, I'm here.
Yes, давайте начинать. Да. Попробуем.
Oh, yes. Yes, we see.
Oh, I think everything. Yeah. So we still wait a couple of minutes, yes? Everything is ready, but let's wait a little bit.
And you can see that part is written in Russian. Christer is a good specialist in languages.
Yeah, I noticed this already.
In Esperanto in particular. In Esperanto.
Я могу читать по-русски, а я очень плохо говорю.
Достаточно хорошо, чтобы было понятно.
Ваше лицо-то появляется только... Оно там на ракетном движении? Нет, он лицо-то распознает, не распознает. Нет, на движении. Вот сейчас, да.
Добрый день.
Добрый день.
Добрый день.
Okay, so I think we will start, yes?
Okay.
Ready? So, okay, let me introduce our speaker today is Christer Kiselmann from the University of Uppsala, and he's going to talk on duality of convolution operators. Okay, please, Christer.
Thank you very much. I'm very happy to join this seminar. And I remember with great pleasure my visit to Ufa in 1989. I will come back to this wonderful visit a little later. So now I'm grateful to be here, although only by electrons, not a physical presence, but a presence through some electrons, a big number of electrons. And as Yuri said, I will speak about duality, and especially about duality for convolution operators. And this duality appears in many situations, in particular concerning convexity theory. And we have first the classical convexity theory in real vector spaces, but there is also a big interest in building a theory of convexity in digital spaces, discrete spaces. And this is a non-trivial problem because there are several different generalizations or theories. And I will first describe duality in a rather informal way and then present several examples. Okay, so this is the plan. First, an introduction, definitions, some properties, some families of functions under duality, and especially second-order difference operators. Because for convexity, we know that second-order differential operators are important. In the discrete case, we don't have differential operators, we have difference operators. And then we have convolution, and finally some future studies and notes. So let me go on with the introduction. So duality means rather a collection of ideas where two sets of mathematical objects confront each other, some kind of opposition. And of course, we have the dual of a norm space, where the linear forms operate on the points, and also the points operate on the linear forms. And we have distribution theory, which is very successful in the theory of partial differential equations. So the distributions work against the space of smooth functions of compact support. All this is well known, and it is a great success in the theory of partial differential equations. And this means that a distribution can sometimes be defined by a locally integrable function, but sometimes not. And as I said, they live like ghosts in the dark, perceptible only through their actions on test functions. And when we have a duality, we keep some properties, but on the other hand, we lose some properties. So a typical example is that a function which is non-zero only in a set of Lebesgue measure, it defines the zero distribution. We cannot see the values in a set of Lebesgue measures zero. And also the support function of a set describes the closed convex set of the closed convex hull of the set, but we cannot see any holes inside the set. So we lose some information. And a rather new branch of science is mathematical morphology. And this theory can help us in, yes? Somebody wanted to make a remark, or?
No.
Okay, very good. So we come to some notions which have their origin in mathematical morphology. So now, if we go on, we need to have the definition of order and pre-order. So a pre-order is reflexive and transitive. It is not necessarily an order. An order we see if we have the next property, meaning that if x is less than or equal to y and y is less than or equal to x, then they are equal. but this, we need not assume this all the time. So this is the order. And what's next? What comes next? Yeah, a very important notion is that of a complete lattice. This is a structure where all families possess an infimum and a supremum. And it is important, the complete means that we can allow also infinite families of sets. So then if we have ordered or even pre-ordered sets, we can define increasing mappings. Here you have the increasing mappings. This is a very elementary property, very important in all kinds of order structures. And we also have the notion of idempotent mapping coming next. Yeah, meaning that if we do the mapping twice, we do not get anything new. So 2 times is the same as 1 time. And also a mapping which is both increasing and idempotent is called an ethnomorphism or a morphological filter. And if it is larger than the identity, we call it a cleistomorphism or a closure operator. And of course, the topological closure is a cleistomorphism. Also, the convex hull is such a mapping. And the opening, to take the interior of a topological space is an anictomorphism. And we will work mainly with the Euclidean plane with coordinates R2, but also the points with integer coordinates, which I call Z2. And they are both abelian groups and with a 0 element. So the important thing is that we can add, and in both cases we have inverses, but we do not need inverses all the time, so we can have semigroups. So abelian semigroup is a good category, but everybody can think about R2 and C2. These are the most important examples. And then if we have a mapping, any mapping, we can in general not define an inverse. This is hopeless in general, but we can define a lower inverse and an upper inverse. And the first with a minus sign, -1 below, this is the lower inverse. We approach the mapping from below, or we've approached the point Y from below by images GX. And the upper inverse, then we approach from above. So we take the infimum of every X such that the value of G is above the given point Y. So these are very important things. And we have studied this a lot. The interesting thing is to ask whether these inverses can serve as left inverses or right inverses, and then we can take the inverse again and we compare the inverse of an inverse with the identity. So these are non-trivial relations. I will not give all the properties. And the oldest thing is 200 years ago, Galois defined Galois correspondences. And this means that we have 2 mappings. They go in opposite directions. They are both decreasing. And if we make the composition, we get increasing mappings, and they are larger than the respective identity. And this is very closely related to the inverses, which I just defined. But of course, since we have decreasing mappings here, we should change the order on one of the sides to get to the other situation with increasing mappings. So this is the oldest property. 200 years ago, the young Galois defined them. And now we have convolution finally. So if we are in a discrete setting, we don't have integrals, but we can sum. So we sum all the products f of y and g of z, where the sum y plus z is equal to x. And of course, in general, this sum cannot be defined. It is infinite and cannot be given a value, but in many cases, it can be given a value. And an interesting question is whether there is a general convolution algebra. But this is a very bad situation, because we have a very simple example which shows that in general we cannot define an associative multiplication, I mean associative convolution product. So I take one function, f equal to 1 identically on the integers. G is a difference operator, which is the Kronecker delta placed at 0 minus the Kronecker delta placed at 1. This is just a difference operator. And h equal to the Heaviside function, which you know from distribution theory. It takes the value 0 to the left and 1 to the right. And then we see that f convolved with g and g convolved with h are well defined. But if we form the product of all three with putting the parentheses in different places, we get different results. So this is hopeless. This is too general. And this means that we have to restrict ourselves in some way. So it's a very fundamental and very bad example. We should be sorry, or maybe we should not be sorry because of this example, but it is a very serious example. And I make the remark that Laurent Schwartz proved many years ago that it is impossible to define an associative multiplication for distributions. And actually, this is the same kind of example if we use the Fourier transformation. So my example here is very elementary, but it is equivalent or can be transported to Laurent Schwartz's famous result. Okay. And of course, we can look at certain special cases. We can form the convolution with the constant function 1. So this is just the sum. And of course, it is an interesting theory of trying to define the sum of series which are not converging. So this is the well-known book by Hardy. He studied series, infinite series, which are not converging. And the best example is the Cesare summability C1, which can be formulated as you see here, this limit, where G is a special function, but we can make this more general. And now we can ask if we can define the sum of a diverging series. We can generalize this question also to other convolution products. So we have some results, some old result by Mailbo and my student Segrel and myself when we studied divergent series. And now this study can be taken up again, and instead of just convolving with one, we can make more general questions about that. So this is a kind of interesting question. And we need a notation for the family of all mappings. I took this from Bourbaki. And also, if we have a zero, we can define f finite, where we assume that the function is, the mapping is zero only, non-zero only in a finite set. And then we have some well-known inequalities for convolution for the L1 functions. So then we also have the LP functions. All this is well known. And for finite functions, the norm is finite, no problem. But we are interested in creating a more general theory where we just don't have finite values, but also functions which are non-zero in an infinite set and even growing very fast. And of course, a simple example is that we have this duality between the finite functions and the general functions. They can work very well against each other. So this is the first and very elementary kind of duality, the F finite against F. But there are many others, and we come to some of them now. Yeah, so we need to define some convolution with an infinite value. So this is just the usual supremum of all finite sums. And therefore we can require a convolution between absolute values to be finite. We can impose this as a condition, which is a very good condition, because it will lead to nice results on commutativity and associativity in the next slide. So if we require that the convolution between the absolute values is finite, then also the convolution without the absolute values is well defined. And we can say a lot of this. So if the first says that if the convolution with the absolute values is finite everywhere, then without the absolute value, it is also well defined, and we have commutativity. And if we have three functions, then we have commutativity and associativity. So this is a very good condition. And therefore, therefore we shall impose this finite thing. And I define this mapping, which I call gamma. So if G is a subset of mappings, then we define F gamma of G as all the functions which work with a finite convolution against everything in G. So this gives a mapping of the sum sets of mappings into the same sum set. And then I can also require that the convolution product shall be, no, you can go back one step. Yeah, the convolution product shall be non-negative. This is a very good condition. So I write this as gamma with upper index non-negative. And then, of course, we can require it to be zero. The next definition is when we get gamma 0, where we require the convolution to be 0 for all elements in G. On the next, this is the next, here is the, right, this is the next definition. And this means that we have tools at our disposal where we can define, for instance, Cauchy-Riemann equations. I mean, discrete Cauchy-Riemann's equations in complex analysis, because we can, of course, also take the complex numbers here and also discrete like z, the integers. So all these are simple variations of this. And this is a very nice theory of discrete holomorphic functions, which I have studied long ago and also again recently. I have studied Cauchy problems for discrete holomorphic functions. So all this comes into this framework of duality, which we have now seen here. And then the mappings gamma and gamma 0 are decreasing. So if we compose in all possible ways, we get increasing mappings. And the figure here at the top, we have the largest gamma composed with gamma 0. And at the bottom, we have gamma 0 composed with gamma in the other order. So these are the 4 possible mappings which we can form by composing. And they are related like this. And we can ask now which are idempotent of these. And also for every gamma 0, gamma, we ask whether they are idempotent or have other properties. So let us go on. Here is a simple property. If we take many families G, J, then we take the intersection of gamma of Gj, and this is equal to the gamma of the union of all the Gj. So this means from this we see that the composition is larger than the identity, and also that the pair is a Galois correspondence. And the same is true also for gamma non-negative and gamma 0. And all this is very easy to prove. So we can we can take a look at the proof. We get one inclusion relation and the other is also very easy. So here is the proof. It is not difficult at all. So this means that we have proved that the identity is less than or equal to the composition gamma ring gamma. Okay. So now we are interested in the fixed point of the cleistomorphisms, because you know the fixed point for the topological closure, these are the closed sets. And the fixed point for the convex hull are the convex sets. So the fixed points are quite interesting as families of sets. And then I make 2 variants of this. In the first here, with the index sub 0, we take G finite. And in the second, we take mu finite. So here mu should be a finite mapping. And we have a non-negative result. Okay, so then we have more Galois correspondences. And the simplest example is the first, which I already mentioned. If we take G0 as the finite mappings and G1 as all the mappings, then they map each other. So the map gamma of G0 is G1 and gamma of G1 is G0. And this means that they are actually idempotent if we take, if we take gamma composed with itself, it is idempotent. So these are fixed points for the second power of gamma. Okay. And then we take a very simple example, the subfamily which consists only of the constant function with value 1. Then gamma of G is L1, the summable functions. And if we go on, we get L infinity, the family of all bounded functions. And then we can go on and form all the higher powers. So we see the higher powers, they oscillate between L1 and L infinity. So these are simple examples of the duality. And this is an interesting observation. If we add all the finite mappings to G, so we form G plus all the finite mappings, then we do not change the value of gamma of this. So we are free to add all kinds of finite mappings. They do not disturb the finiteness condition, of course. And this means that we can define gamma on a quotient space. The quotient space comes here. Yeah, this is the quotient space. We take F, all mappings, modulo the finite mappings. And this is a very interesting space. It is analogous to the space of singularities, the distributions modulo the smooth functions. And also more elementary, we can take the continuous functions modulo the smooth functions. And these are topological vector spaces, but they are not Hausdorff spaces. And often in textbooks, the author immediately makes the assumption that the vector space is Hausdorff. But I think this is premature. These non-Hausdorff spaces are very interesting, and I think they are worth some extra study. Not now, not in this lecture. Okay, so for one variable, we can say a lot of things because it is an easy case. So we form the gamma zero for any given class and all the higher powers, and also all the variants with gamma zero, gamma non-negative. And what do we get? Well, we can take only one function with finite support, beta, and we can assume that it starts with a non-zero value at the origin, and then it has the structure Kronecker delta placed at 0 minus gamma, and then we get a nice inverse because we can form a converging series of all the powers of gamma. The powers of gamma define a converging series. Very nice, converging in the very best way. So the sum is given, here it is. So we take the sum of all the powers of gamma. This is a geometric series which converges perfectly. But an interesting question is now if this inverse has finite support or not. So this is, and here I described gamma zero, which is given by a functional equation, gamma star f equal to f, which I can call a kind of periodicity. And we now can describe that the second power is equal to the all functions mu, which satisfy the conditions which I write here. So mu against f shall be 0 for all f which satisfy these finiteness conditions. And then we can describe more closely this inverse. So again, we have a kind of periodicity. Rho star gamma is equal to rho plus gamma. You have to think about this as a periodicity. So the property now, the answer to the question I asked is in the next slide. And I cannot say so much in general, but for special choices of beta, we can analyze the situation, and we get the following. Yeah, first we need the Heaviside function, which is 0 to the left of some point and 1 to the right. And then this is an inverse of the difference operator. So if we take the convolution with the difference operator, we get the Kronecker delta to place A. And this means that we can solve several simple convolution equations. So here is a first example. If I take beta equal to the difference operator, delta 0 minus delta 1, then gamma 0 is just equal to the set of all constant functions. These are the functions which have difference 0, obvious. Very simple. And now we take the higher power. Then we have three properties which are all equivalent. I call them A1, A2, and A3. So the first is that mu belongs to the second power of beta. The second is that the sum of mu shall be 0. And the third is that mu is the product with a function nu, which is finite. So mu is equal to beta convolved with nu finite. And this is easy to see. So we can just take a look at the proof. It is not difficult at all. Okay. And now, yeah, please go on. So these are the three properties. This is the proof. And now we take a new example. Now I take the difference operator, but convolved with itself. So it's the second power of the difference operator. And then we see that the solutions to the convolution equation beta star f equal to 0, these are exactly the restrictions to the integers of the affine functions. And this is yeah, and now we have three properties, which I call B1. So the first is that mu belongs to the second power of beta. The second is that it gives the result 0 against all affine functions, or more precisely, restrictions to the integers of affine functions. And the second is, as before, the third is, as before, that beta is, mu is equal to beta convolved with nu finite. And this is also quite easy to see. Yeah. So, and now we take a third example, and this is more interesting because it is related to convexity. So here I take the gamma with non-negative and study the higher powers. So the first set, which I describe here, this is just the restrictions of real-valued convex functions. So we take the convex functions on the real axis, we restrict them to the integers. This is a nice example. And the second, when we take the second power, it is of the form beta convolved with sigma, where sigma is finite and satisfies the condition non-negativity. And then when we take the higher powers, we oscillate between this second power and the restrictions of convex functions. So this is a very nice example, and it shows the importance of the duality when we want to study discrete convexity. And discrete convexity in this case, when we have Z, is very simple. And here we have more precisely what I more or less said, the three conditions which I now call C1, C2, and C3. So this is a result similar to the other one with A and B. And this is also not so difficult to see. Here we see the proof. And here we go back, please. We see that here in the big formula, I need the associativity. And we know that associativity is something very dangerous. But in this case, it works well, because here we have factors which are 0 for large negative arguments, and then convolution is very easy to define, and associativity, commutativity are easy to define. I mentioned this. So we have, if you have support in a strict cone, you can work very easily with convolution. Okay. Yeah, this is the proof that the sigma has finite support. Okay, so let me take a look now at a similar case where we have duality between functions and second order difference operators, because we saw that one second order differential operator is important for convexity, but there are many such operators, all defined, as you see, G equal to a sum of Kronecker deltas, delta 0 minus delta at minus A minus delta at minus B plus delta at minus A minus B. This is a second order difference operator, which is quite important. And we saw already a simple example of that before, but now we have lots of choices because A and B can be chosen freely. And therefore I define two mappings which I call phi and psi. And you see here, the first is phi of A. If we take a number of points A and B, we require that the difference operator shall give a non-negative result. And for psi, in the other direction, we look at all possible choices of A and B, such that the result is non-negative for all functions in G. So they go, phi and psi go in different directions against each other. And therefore it is interesting to form the compositions of phi and psi in both directions. I think there will be some. Yeah, now we can look at a generalization of discrete convexity just by using convolution. So I say that a function is M positive, where M is any set of functions, if the result F star mu is non-negative for all choices of mu in the big set M. M can be a singleton set or a very large set. And the important thing, of course, is that it should be finite so that the convolution is well defined. So the simplest example, of course, is we take just Kronecker delta. Then mu positive means that the function is non-negative everywhere. More interesting is if we take this, which we use for convexity, then the condition is exactly that F is convex extendable, meaning that it is the restriction of a convex function. So this is a nice example. But we know that the constant functions are convex, so it is natural to require that all constants shall be M positive. This means that the negative part and the positive part shall have the same mass. So if we sum the negative part and the positive part, we get the same result. So there is an equilibrium. And this is the necessary and sufficient condition for all constants to be M positive. And next, we also know that all linear functions are convex. And what does this mean? Well, we can define in a very natural way the barycenter, the point where the mass is concentrated, the barycenter, and they shall be equal. Of course, if mu is 0, we cannot do it. But if mu is non-zero, the positive part and the negative part shall have the same barycenter. So these are very natural conditions. So this means that we have this for all affine functions, meaning constant function plus linear functions, that the negative and positive part shall have the same mass and the same barycenter. So this is very natural to assume. Okay, then there is another property for convex functions in a real space, namely that if both f and g are convex, then also the supremum is convex. So not only the sum, but also the supremum. And to find this property, I formulate the following lemma. So if we take a function which is finite, but not 0, then there is a natural number such that for all polynomials of degree at most m-1, we get 0, but for a polynomial, some polynomial, we get a non-zero result, which we can take to be the constant 1. And I can prove this using Fourier analysis, because we have the Fourier transform, mu hat, which I write here. And if we differentiate it, it means that the convolution with all monomials, if the convolution is 0 against all monomials of any power, then all derivatives of mu hat vanish at the origin. And since mu hat is an entire function, this implies that mu is 0. So this proves the lemma, and now we can get the result which I wanted. This, this is just what I said. We can get a constant for lower ordered polynomials, but a constant, non-zero constant for the order m. And in the cases we are studying, then m should be at least 2, but in practice it can be very large. So now we have the theorem. So we take first a set, any set of finite functions with finite support, and they shall annihilate all affine functions. This was a natural property, as we saw. And then if the negative part is a singleton set, I mean, it's non-zero only in a single point, then we can form freely the supremum of any family of M-positive functions. And the supremum is also M-positive. So this is one direction. Now we go in the other direction. And then if I take a mu, non-zero, which annihilates all affine functions, and such that this mu has this property that the supremum is mu positive for all functions which are mu positives, then the support of the negative part must be a singleton set. Now you see that unfortunately this is not a full converse, because I prove it only for one non-zero function. I should have something for a family. And now for the first direction, we always have this, these inequalities. And now we take the supremum of the left-hand side. So we get the second formula, inequality. And we have a general inequality, mu minus star f is a majorant of the supremum. But if the support of mu minus is a singleton set, this is actually an equality. So we get what we wanted. So the supremum is actually M positive. And in the other direction, it is more complicated. So I now need the lemma with M and the polynomial Q. And then there are 2 points. We assume by contradiction that there are 2 different points where mu is negative. So we shall now reach a contradiction. So mu of A is negative and mu of B is negative. And we can, since it's finite, we can assume that the first value is the minimum. And then I form the delta placed at minus A plus a constant times Q, this polynomial of degree M, and also G as the polynomial, the same polynomial, but and the Dirac, the Kronecker delta placed at minus B. And then I have this formula for the supremum. So you see the supremum is just the sum of the 2 Kronecker deltas plus the same polynomial, only once, not twice. So A of Q appears. And then I can now compare. The constant A is not defined yet. So I calculate a little, and then I see that with a special choice of capital A equal to mu minus mu of A, which is the minus the minimum of mu. And then we get an inequality. And this is all true. And so that mu of A plus X is larger than, or at least equal to mu of A, and mu of B plus X is at least equal to this. But the sum is not. And this is a contradiction, and the contradictions proves the theorem. So I think this is a nice result, which illustrates the difficulties and also the positive results for discrete convexity, which is, I think, quite an interesting topic. Okay, so let me be brief here that I studied with my PhD student Shiva Samiania dualities of this kind. and with difference operators of second order. And I think that this is a study which could be extended, and you are welcome to try to extend it. So, as I said, you're welcome to continue this and extend it. And also, we studied the marginal functions of functions with real values, but it is more difficult to study functions with integer values, and also functions which are defined on general discrete sets, not just at the integer points. So there are things to do. And this is a bit different from what I talked about. I added this because Yuri asked about quasi-crystals. So we take an affine function of the form gamma x plus a constant. And then we discretize it by taking the floor function. So little f is the floor function of capital F. We go down to the nearest integer. And then we subtract again the linear function gamma times x. And then we have several different equivalent properties coming up. So gamma rational, f sub gamma periodic as a function, the image of f a periodic set, and the difference d1 defined like this is a periodic function. So all these are equivalent. And this is not very difficult to prove. And the interesting thing here is that if we project the graph of f on the first coordinate, we just receive the set of integers, which is very periodic, period 1. If we project on the second coordinate, then we receive the image, which is not periodic if and only if gamma is irrational. So this means that we have an object, which is a very easy object, the graph of this function with integer values, which is a kind of primitive example. If you look at it from one side, it is periodic. If you look at it from the other side, it is not periodic. And this is something which Danny Shechtman studied. He found the quasi-crystals in chemistry and got the Nobel Prize in chemistry. And I think that the quasi-crystals is a very difficult but very interesting topic. Okay, so let me make a few notes that the discrete convexity and related things have been studied by many mathematicians. So we have lots of duality problems, too many. I mentioned some of them, but let me also mention some other mathematicians which you can look up sometimes. There are functions which are called M-convex and L-convex, which have been studied by Murata and collaborators, Murata and some other Japanese mathematicians. And they have studied the notion of supermodular and submodular functions. So, and also how these behave under the Fenchel transformation, which is the main duality for convex functions. So there is a lot of literature which you can look up. If you want, I can send you some files with more detailed information. I just want to tell you that I'm not alone in this. In particular, Murata has a book on discrete convexity. Yeah, and here are some Fuji Shige and Murata and Shiura and Murata. these are other Japanese mathematicians which have been working together with Morota. So thank you very much. I can also mention a very simple duality between lines in R2 and the coefficients. So a line is given by y equal to alpha times x plus beta, where the two parameters are alpha and beta, and then they pass through a given point PQ if and only if P and Q satisfy this relation. And they define, now if you fix P and Q, they define a straight line in the dual plane of the alpha and beta. So this is a classical duality, and it's called a Hough transform in digital geometry with a reference given here. So these are also convexity marginal function is an interesting topic, which, as I already mentioned, could be extended. And I mentioned a reference to my PhD student. He proved a special case of the theorem on M convexity, namely that he had a case where the polynomial had degree 2 and that the minimum is attained only in one point. And now I have eliminated these special hypotheses which were not necessary. So Adama Aruna Kone works in Mali. I have been there twice. So this is my conclusion. I hope that I have shown to you that it is a useful tool when studying convexity, both in real vector spaces and in the many efforts to create a theory of discrete convexity. So this is pairs of families. Now, to my pleasant memory, it is a great memory. I was in the Soviet Union in Moscow, Ufa, and Tashkent in October and November in 1989. And I was invited then by Valentin Napalkov, whose name comes up here, Valentin Vasilievich Napalkov, and I met Rinad Yulmuhamedov and also Igor Krashikov-Tarnovsky, who unfortunately died in 2012. And I would also like to mention Alexei Krivosheyev, who did very nice work on convolution equations, Alexei Sekerin, who unfortunately died in 2008, according to Yuri, and Sergei Papionov. And we made a very nice excursion to the Ural Mountains. We had lunch with potatoes baked over an open fire in the snow. It was October, but the snow was already there. And we were driven by a big vehicle, four-wheel drive, which was kind of necessary in these conditions. This is a lovely memory. So thank you very much. And now today I'm invited by Yuri, and I'm very grateful for this invitation. Большое спасибо.
Okay, so thank you very much. Let's send the speaker.
Да, конечно.
Now questions. Please ask questions.
There is a question from Nizhny Novgorod.
Nizhny Novgorod, hello.
Have you tried to apply your results for the image processing?
The result follows.
Have you tried to apply your results for image processing?
Yes, indeed. Very good question. I'm happy to say that I'm writing a book which contains lots of applications to image processing. So in image analysis, I work with people. I don't do so much applications in image analysis, but I work with people in image analysis, image processing. And I have a book with 477 pages, which will come out in Singapore, World Scientific in Singapore. So is it more or less ready? I will submit it finally, but I have a contract with Singapore and I'm very happy with this. I have visited Singapore twice. It's a wonderful place, both intellectually and scientifically in all ways. So thank you for this wonderful question.
Thank you.
Okay. More questions?
Yes, may I say a few words? First of all, thank you very much for a very interesting lecture. In some sense, you gave an overview of the whole theory. We now can understand how we can apply it. I first met this convolution, discrete convolution on discrete abelian groups when working with John von Neumann group algebras. And I think they have, not I think, but I know that they are very important when you consider Hamiltonian translation invariant Hamiltonians, which is a very close relations to different problems in physics. Yuri also knows about it, and to quantum Hall effect and topological insulators and so on and so on. Did you work with that, or do you have some knowledge about that?
No, I'm sorry to say that I have not. I'm not so good at theoretical physics and Hamiltonians and stuff, but I have seen your papers and other papers on this kind of duality, and so I appreciate it, but I have not worked myself on this.
But you mentioned quasi-crystals. That's also very interesting and very important, I think.
Yes, indeed. And I went actually to Haifa, and Danny Schechtman accepted me some years ago. He is a wonderful guy, very friendly, and he explained how he discovered this. First it was, contested and criticized, and then suddenly he got the Nobel Prize. So, so you see, things can change very quickly. But, and I have my mathematical brothers, Ragnar Sigurdsson and John Boman. We are very interested in quasi-crystals, but we have not done very much research. We have more or less scratched the surface, done some very elementary things. But it is an extremely interesting problem because it relates properties in the space and the dual space of Fourier transforms. So the Fourier transforms of periodic sets and aperiodic sets are very interesting. So I really want to make propaganda for this, but I don't have very many results. Thank you.
Okay, thank you, thank you.
Okay, more questions? So?
Okay.
Okay, so let me ask one question maybe. Are there any analogs of this theory for continuous objects, say for complex numbers, or not for discretes? Or
yes, of course, for convexity theory in real spaces, it is a highly developed theory, with starting perhaps with Fenchel. The Fenchel transformation for convex functions and the support functions. This is highly developed. So in my book, I start with real convexity as a model. And then I go on to discrete convexity and try to imitate the results from real convexity, the well-known results.
Yeah, I understand. So in some sense, discrete case is more complicated because of discreteness here.
Absolutely right. I have several examples where discrete mathematics is much more difficult than continuous based on real or complex numbers. Right, very good observation.
And you were talking only about Z2, but you can also consider more complicated objects as far as I understand.
Yeah. For in my book or in other papers, I consider all dimensions, but of course for the lecture, I thought it was easier to have just the two-dimensional.
I mean, not only dimension, but also more complicated lattices like
Yes,
or,
yes, also that, yes.
I see. Okay, more questions, comments? Okay, if not, let's thank the speaker again.
Thank you very much.
Thank you, Christopher. Was very happy to see you.
I'm very glad to see you again after so many years. Thank you so much.
Yes.
Okay.
Okay, thank you. See you again.
Then we can stop the demonstration, I guess, yeah?
Yeah.
Yes.
So if you want some papers, you can write me, I can send you.
Yeah, okay.
Paper.
Also, we have a presentation, and we have also recorded your lecture, actually. So.
Okay. Okay. Thank you.
Thank you.
Thank you.